Hello, this is Mr. Moss, and in this video, we're going to be learning all about angles. Some of you may have some prior knowledge about angles, and for other people, this might be really your first time learning about angles. Either way, we're going to learn all about them. But before we get started, I thought it might be fun for us to relax and open up with a fun music video. So without further ado, take it away, Mrs. Borio.
It's electric. This is the electric slide. You can't see it. It's electric. You gotta feel it. It's electric. Ooh, just feel it. It's electric. You gotta miss the feeling with the fucking electric energy. The moving like electric. You gotta know it. It's electric. Want it. Now you can't hold it. It's electric. Want it. But you know it's there. Here, there, and everywhere.
Wow, that was terrific. Thank you so much, Mrs. Borio. And you know what I noticed? She kept changing directions. She started off first facing to the left, then she was facing upward, then she was facing to the right, and then finally she seemed to be facing downward. And it made me think, we use a lot of different ways to represent four directions, four different angles that somebody could face. Sometimes we use the directions up, down, left, and right, like what you might see on your keyboard. But we use other ways of representing these also. Sometimes on a map, we use our four cardinal map directions: north, south, west, and east. Those give us four directions to travel on a map. Sometimes we use the numbers on a clock face to help us out. Something that's straight in front of you is 12 o'clock. Something that's to your left is 9 o'clock, or to your right is 3 o'clock, or to your rear is 6 o'clock. We use those numbers to help us out. But we can also use fractions to help us to think about turns. Because just as Mrs. Borio was moving in four different directions, we know that if we take a whole circle or a whole turn and divide it into four parts, each of those parts is a fourth. Let's learn a little bit more about this. So I have my Lego friends here to help me out with this idea of how fractions can represent turns. I'm going to take my minifig right here, and I'm going to have him face away from us for just a moment. So right now, he's facing away. That's his starting point. If I have him turn, we can say that he's made a quarter turn, because a full turn would be him going all the way around. So just one turn is 1/4 of that. It's a quarter turn. And we'd say that it's a quarter turn clockwise because think about how the hands in a clock travel. They turn around in this direction. So this is a quarter turn clockwise. I could go back to my starting point here. And if I want to have him turn like this, that's a half turn. He's made 1/2 of a complete rotation. So this is a half turn. And again, I went clockwise. If I start from the beginning and I have him turn like this, we've got a quarter turn, a half turn. So this would be a 3/4 clockwise turn. And finally, we can start at the beginning and do a quarter, half, 3/4, and finally, one full turn. That was clockwise. If I go in the other direction, we call it counterclockwise. So here we have a quarter turn counterclockwise, a 3/4 turn, a half turn counterclockwise. This is a 3/4 turn counterclockwise. And now we're back at the beginning with the full turn. You'll notice that sometimes they can line up. For example, if I position my minifig facing to the right here, that could be both a quarter turn clockwise, but it could also be a 3/4 turn counterclockwise. So there's definitely some overlap in what this means. But The idea of being able to take a full turn, a full circle, and divide it up into fractions, in this case fourths, to get a quarter, half, three-quarter, or a full turn can really help us to understand the beginnings of angles. Let's take a moment to learn about how an angle might look on a sheet of paper. So if I'm drawing a quarter turn angle, I'm going to draw one side, and then I'm going to draw the other side. And whenever you're making an angle on paper, you need to show something called an angle arc, and that's to show which way it's opening. Now, normally for your average angle, that's going to be curved, but because we learned that perpendicular line segments, lines, and rays can fit a square in the intersection here, we're going to use a square-shaped angle arc. So this right here is a quarter turn. Here's the problem, though. I know from what we were just talking about that I can have a quarter turn. I'm going to just freehand them here. I can have a quarter turn. I could have a half turn. I could even have a three-quarter turn that goes all the way around almost. But what if I want something in between? For example, what if I have an angle that I want to make travel up this way in between? So if I want to have an angle that looks kind of like this, I can't represent that with a quarter turn or a half turn or a three-quarter turn or a full turn. I need something more precise. That's the problem with only using 4 directions for an angle. We need a better solution. The only problem is that not every angle, not every turn works out by being divided perfectly into 4 different parts. Sometimes we need more precision. Let's take a look at an example. We've got a delicious pizza right over here, and you can see that cutting this pizza into fourths may not work. I don't think I've ever seen a pizza cut into 4 slices. They'd be so large. And instead, this particular pizza is being cut into 8 slices or eighths. That's getting a bit closer, and that's going to allow me to have a delicious slice of pizza. Take a look at another example. We talked about compass roses a moment ago that help us to know our map directions, north, south, west, and east. Well, it's not limited to north, south, west, and east. There are those in-between directions, northwest, northeast, southwest, and southeast. Again, the idea of having 8 directions. In fact, some people have ones that are even in between those. But still, 8 directions, that's got to help us out. Dividing a full turn into 8 parts, that's a lot better than only 4 parts or 4 quarters. Eighths are a lot closer. Still, we're going to need even more precision. So let's look at some other options as well. I'm looking here at this clock face, and I notice that we're taking a full circle and we're dividing it into 12ths. Each of those 12 parts, that's a lot smaller than fourths, that's smaller than eighths. We're now down to 12ths. We're getting closer. And yet still, you can see there are plenty of spaces in between each of those 12ths where we can again get more precision than just having a circle divided into 12ths. We can divide it into 60ths. We can again use a clock to help us out, but instead of using the 12 main parts, or even the 12 hours in a clock, we can use the 60ths that help us to figure out how we can divide an hour into 60 minutes or a minute into 60 seconds. So you can see right here, this is showing us how we can divide it up, and you can see each of those slices is so much smaller than when we only divided the whole circle into 4 parts or 8 parts or even 12 parts. 60ths are way smaller. You can see it shown right here. And yet still, we may need more precision. There are so many situations in the real world where dividing a circle into 60ths still isn't adequate. So one example could be that if you're doing woodworking or building a building or anything else where you need that precise angle, you need to have more precision. So let's take a look at another option. This is a protractor. Protractor is a tool used to measure how big an angle is. And you can see that we're looking at a full circle and it's divided it into 360 degrees. Each of these little parts we call a degree, and we symbolize them with that little circle to the right of the number. And these 360 degrees are awfully precise. Just one of those little pieces, you can see an example shown right over there, is 1/360th of a full turn or of a full circle. Let's zoom in and take a look right now. This bright green line shows us 1 degree, 2 degrees, 3 degrees. This is 4 degrees. And finally, here's 5 degrees. Look how narrow each of those are. That helps us to have more precision. Can you imagine if this was a pizza and you were getting a slice that was 1 degree big? It would be a tiny slice. But in this case, those tiny slices mean that we have a more precise measurement. They help us out. So if we zoom back out again, let's take a look at 90 degrees. 90 degrees is the same as a quarter turn. So when Mrs. Boria was dancing earlier and we were looking at quarter turns, we can also call that 90 degrees. So there's a quarter turn, a half turn, a 3/4 turn, and a whole turn, one full turn or one full circle. But we can express that instead of using fractions of fourths of turns, we can also represent that in terms of degrees. A quarter turn, like I just said, is 90 degrees. So 2/4 turns or a half turn is 90 degrees plus another 90 degrees. That's 180 degrees. If I have 3/4 turns, that's 90 plus 90 plus 90, that's 270 degrees. And finally, 4/4 turns or one full turn is 90 plus 90 plus 90 plus 90, which equals 360 degrees. One full turn, one full circle is 360 degrees. Let's look at some examples now of how I can have different angles to show different sizes. So right here, you can see that I'm showing you a quarter turn or 90-degree angle. But not all angles are going to be exactly 90 degrees. Some are going to be smaller, like this angle. It's only 25 degrees. This angle is 49 degrees. It's getting a little bigger. This one's almost a quarter turn. It's almost 90 degrees. It's 82 degrees. This angle's a small one. It's only 10 degrees. Some angles are going to be larger than a 90-degree angle. This one, whoa, that's pretty big. That's 143 degrees. This one's 112 degrees. This one's 124. You'll notice that they can open in any direction. They can face any which way. That one's a little bit bigger, 126 degrees. Oh my goodness, this one is almost a half turn. This is 178 degrees. It's really, really close to being 180 degrees, which is a half turn. You can have angles that are larger than a half turn. For example, this one right here is a bit bigger. That's 192 degrees. This one's quite a bit larger. This is almost a 3/4 turn. That's 259 degrees. This one's only 243 degrees, still almost a 3/4 turn. And then finally, you can have some that are even larger than a 3/4 turn. You can have this one, it's 290 degrees, 309. Look at these different angles. Some are getting a little bit bigger, some are getting a little bit smaller. Oh, whoa, look at this one here. This one's almost a complete turn. We know that a complete turn, a full circle, is 360 degrees. This one is just shy of that. It's 357 degrees. So as you can see, we have lots of different kinds of angles when you've got 360 degrees to work from, but it can get a little bit confusing to have to look at each of these angles and just consider every single measurement in degrees as its own thing. There's got to be a way to somehow sort these and organize them into different types of angles. So first, let's talk about a new term for us to know. We've been drawing a lot of 90-degree angles. We've been drawing these quarter turns, and there's a name for this kind of an angle. We call this a right angle, and that's exactly what it is. It's a turn that's a quarter turn, or it's 90 degrees. Something important to remember about right angles is that they don't face just one direction. I could have a right angle that goes this way. I could have a right angle that goes this way, and they don't even have to end up being straight. What's important, though, is that you can end up fitting a precise square inside of that intersection. So I could draw a right angle that goes kind of diagonal, but still, I'm going to make absolutely sure, to the best of my freehanding abilities, that I could make this a 90-degree angle inside, and that I can symbolize that using my square-shaped angle arc. The thing to remember about a right angle is no matter which way you're placing it, no matter which way it's pointing, it's still always exactly 90 degrees, or a quarter turn. Not 89, not 91. It is precisely 90 degrees. If you have an angle that's smaller than a right angle, we call that an acute angle. An acute angle is less than 90 degrees. It's less than a quarter turn. So for example, I have an angle right here that I'm drawing. It's smaller than a right angle. It's not an eighth of a turn. I don't know what fraction this is, but it's less than 90 degrees. It's less than a quarter turn, so that's an acute angle. They can open up to the right, but they can also open up to the left. You'll notice that this angle is quite a bit larger in measure than that first angle I drew. This first angle only opens a little bit. This angle here opens up quite a bit more, and yet it's still less than a 90-degree turn. It's less than a right angle. A right angle would be probably right about here or so. This would be a right angle, and this is quite a bit smaller. So it's an acute angle. They can open to the left, they can open to the right, and just like right angles, an acute angle can face any direction you want. They can even go downward, upward. The sides don't even have to be the exact same length. I'll draw you one more acute angle here. I can have an acute angle where one side is really short and the other side is a little bit longer. It still is an acute angle here as long as it's less in size than a right angle, as long as it's less than 90 degrees. That makes it an acute angle. A good way to remember what an acute angle is, by the way, is to look at the name. Sometimes we look at, little babies, they're so small, and we say, oh, they're so cute, right? And an acute angle is a small angle. It's the smallest kind of angle because it is smaller than our right angle. So let's take a look at some acute angles. Here's one that's 7 degrees, very, very small. Here's one that's a bit larger, 52 degrees, 47 degrees, 20 degrees, 11 degrees, 21 degrees, 9 degrees. So you can see all of these acute angles, no matter which way they're facing, every single one of them is between 1 degree and 89 degrees. They're all smaller than a right angle. They're all smaller than a quarter turn. That's what makes them acute angles. If you have an angle, however, that's bigger than a right angle, we call that an obtuse angle. So we know that a right angle is 90 degrees. So an obtuse angle starts at 91 degrees and it gets bigger and bigger. So here's a good example of an obtuse angle. It's really close to being a right angle. It's almost 90 degrees, but in fact, you can see that it's a bit larger. A right angle would probably go up like this or so. And so this obtuse angle here is ever so slightly larger than a right angle. So an obtuse angle is greater than 90 degrees, but it's less than 180. So if I draw you another one, this is a very large obtuse angle. You can see it's almost close to being a half turn, but yet it's not quite a half turn. It's a bit smaller than that, and that makes this an obtuse angle. Just like the other examples that I drew, an obtuse angle can go in either direction. It doesn't need to necessarily be straight. Your sides can be different lengths. So here's another good example of an obtuse angle. And here's another one. So again, an obtuse angle is greater than 90 degrees. So it starts at about 91 degrees, assuming we're not going into a decimal. And it's less than 180 degrees. It's less than a half turn. That makes this an obtuse angle. Let's take a look at some obtuse angles. This obtuse angle measures 100 degrees. It's bigger than a right angle, but it's smaller than a straight angle. This one is 119 degrees, 104 degrees, 152. This is a lot larger than the others. This is pretty close to being a straight angle, but still it's in between a right angle and a straight angle. 109 degrees, 171, that's awfully close to being a straight angle. Still not there yet. All of these are obtuse angles because they're greater than a right angle, but smaller than a straight angle. And that makes them an obtuse angle. Straight angles. Much like a right angle, a straight angle is one specific kind. It's not a range of possible angles. A straight angle, start from your starting point. And so you've got here an angle that measures exactly 180 degrees. So it is exactly a half turn. It opens up all the way around. A straight angle could be facing in either direction. You might look at this and say, well, gee, that's just a line right there. And that's a good point. You know, we would look at what I'm drawing right here, thinking about lines, line segments, and rays. That looks like a line, except it's going through this vertex right here. And it's opening up halfway. I could have my same straight angle, by the way. If I draw one more here, with my vertex, my point in the middle, I could have it open downward. Maybe it's going that way, up and around. That's a straight angle as well. But again, straight angles are exactly 180 degrees, no larger, no smaller. They are exactly 180 degrees. They are exactly a half turn. Finally, let's talk about a reflex angle. A reflex angle is greater than 180 degrees. So for example, here's one side of my angle, and I know that if I had the other side right here, I'd have an acute angle. If I had it here, it would be a right angle. Oh, now it's an obtuse angle. We're getting larger. Obtuse, 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 obtuse. Now it's a straight angle. As soon as it gets bigger than 180, we now call that a reflex angle. Now, this is a great example of why the angle arc is important, because this is showing me that my reflex angle gets larger and larger and larger and larger and larger. Somebody might look in and say, well, gee, that's just an obtuse angle right there. And that's true. This part of it right over here is an obtuse angle, kind of upside down. But if I show you another good example here, hold on one second. Somebody might look at this and say, this is an obtuse angle. And indeed, until I draw my angle arc, I don't know, am I looking at an obtuse angle here, or am I looking at a reflex angle here? So that's the tricky part. That's why we always, every time we draw an angle, we need to draw an angle arc. I'm going to show you another example right over here. So somebody might look at that and say, that looks like an acute angle. And you're right, it sure does to me, but that's an acute angle if I put my angle arc right over here. If my angle arc goes around the outside of my angle, it shows me I'm paying attention to this outer measurement and that this is a reflex angle because it's greater than 180. This is almost a full turn. Last example here for you. Somebody might look here and say that I'm drawing for you a right angle. It could be a right angle. If I'm looking at this internal measurement, this is a right angle. But in this example, I'm looking at my outer measurement. It's a reflex angle. This is actually a 270-degree angle going around the outside because it's 3 of those 90-degree angles put together. 1, 2, 3, right over here. So again, a reflex angle, anything greater than 180 degrees. Let's take a look at some real-world examples of acute, right, obtuse, straight, or reflex angles. Here's a terrific photo of Fenway Park taken from a helicopter looking down at a game between the Boston Red Sox and the New York Yankees. Let's zoom in and get a closer look. So you can see there are players all throughout the field, and if you look closely, you can see 2 white lines that are perpendicular to one another. Those are the foul lines. I'm going to show them to you in a bit more detail right now. So these red lines show where the foul lines are. And I might ask you, what kind of an angle is this? Well, if you're having trouble answering, you're right. We don't have enough information yet. It depends how you look at this angle. For example, if we look at this as a right angle using the 90-degree side on the infield and on the outfield, then that's going to show us where a ball could land if the batter hit it and have it be a fair ball. If the ball travels anywhere in between those 2 blue lines, it's a fair ball. But let's look at the other angle. Now we have a reflex angle. It's 270 degrees, and that shows the area outside the foul lines where if the ball lands, it's a foul ball. You'll notice it goes all the way around from one foul line back behind home plate over to the other foul line. So really, it matters whether we're looking at this as a reflex angle, in which case it's a foul ball, versus a right angle, in which case it's a fair ball. The 2 angle types really matter in baseball. So for this next example, I want to teach you about something called supplementary angles. Right here, you see 2 angles that connect across a line. And as I make one of these angles larger, like angle B, angle A gets smaller. On the other hand, if I make angle B smaller, A gets larger. And that's an important thing to know because we can say that at the beginning, they're both right angles. But as soon as A becomes an acute angle, B becomes an obtuse angle. If A becomes an even smaller acute angle, B becomes a bigger obtuse angle. If A is a super tiny acute angle, B is an awfully large obtuse angle. And again, all of this works on the other side. As A grows into a larger and larger obtuse angle, B shrinks into a smaller and smaller acute angle. And again, these are called supplementary angles. That when you put these 2 angles together, they're going to equal 180 degrees. They make a straight angle. So here's why we were just talking about that. Here we have an aerial view looking down at a building. Do you recognize what we're looking at? Well, this is nothing other than Roaring Brook School in Avon, Connecticut. And at Roaring Brook School, you can see that this driveway leads into a street that's going right down here. This is Old Wheeler Lane. And if we move a little bit, you can see that Old Wheeler Lane, which is right over here, intersects with another road called Lovely Street. Right here, where Old Wheeler and Lovely intersect, you can see that we have an acute angle here. And that means that the other side, we have an obtuse angle. Yes, with angles, you're always using line segments, lines, and rays. And as you know, those have to be straight, which Lovely Street here and Old Wheeler aren't perfectly straight. But still, we can recognize that this is an acute angle, and we can recognize that this is an obtuse angle. Let's take a look on a map, and it'll be a little bit more clear for you. You can see right over here on Old Wheeler Lane, where it intersects with Lovely Street, you've got an acute angle here, and we've got an obtuse angle right over here. You can see that where Old Wheeler Lane intersects with Old Wheeler Court, it's just about a right angle, except I think it's a little bit large on this side. I think it's ever so slightly an obtuse angle. But if we move a little bit, you can see that Lovely Street intersects with Country Club Road. Now this looks to be a very clear right angle, just about 90 degrees, I think. Where Old Wheeler Lane intersects with Country Club Road, it's close to a right angle. Maybe it's not a perfect right angle. Maybe neither of these are truly perfect right angles, but they sure are close. Same right over here where Camelot Lane intersects with Old Wheeler Lane. Looking at maps can be really interesting to look for the different types of angles. These are just a few of the many examples of where you'll find different types of angles in the real world setting. This is such an important skill for you to have, and it's something that you will use throughout your entire life. In this lesson, you learned about the different angle types: acute, right, obtuse, straight, and reflex. You learned what makes them similar to one another and what makes them different, and I hope now you're able to spot them not just when you see it on paper or on a computer, but also if you see them in the real world. This has been Mr. Moss, and I hope this was a helpful guide for you. Have a great day.